welcome to our next video. So for today's topic, we're going to be looking at continuity. So we spent the first two sections looking at limits of functions. Today we're going to take that concept of a limit and uh, apply it to be able to investigate whether a function is said to be continuous or not at a point and then over an interval. So the topic of continuity has come up a little bit through the first two sections, but we haven't formally defined it or looked at specific examples just yet. And that's really what we're going to take a look at today. So to start, we're going to talk about continuity at a point. So the formal definition is a function is continuous at a particular value of x, and we're going to call that c. When we say that, it means that there's no interruption in the graph at x equals c, or visually, the graph is unbroken at that value. A simple way to think about it is if you trace over the graph, you should be able to pass through the point or the value on the graph of the function at x equals c and never actually have to pick up your pencil or pen to continue tracing. So what we have here are three examples of graphs that are not continuous. So for the first one, this is referred to as a non-removable discontinuity, or more commonly, a hole. Goes by both. Non-removable discontinuity is the more formal name of it, but then we've got a hole for a much simpler, easier way to refer to it. But again, you can see if I were tracing along here, I would have to pick up my pen or pencil to jump over this removed point from the graph and then move on. So the big issue here is that the function is not actually defined at that value of x equals c. Second one, the function is defined at x equals c. You have a defined point up here, but this would be a break or a jump discontinuity where the graph is actually broken into two pieces around that value of x. So when tracing, I'd have to pick up and jump down from the first piece down to the second to continue on tracing. So another issue with continuity there. And then this guy, this one's also a hole or removable discontinuity, but it's like an extra point is defined elsewhere. So it's like a way of manipulating this first example. This is not a naturally existing scenario. This is something that's accomplished by working with a piecewise function. So it's pretty evident when this exists, and we'll pick up on ways to recognize that throughout the course. But this would be another one. The only way to graph this or trace it would be to trace the first chunk, jump down to this point, and then jump back up and continue tracing on. So all of these are examples of functions that are not continuous. But the idea is we want to be able to recognize formally and mathematically how or when a function is continuous. So to do that, we have three conditions. So the formal definition of continuity at a point is that a function f is continuous at c if the following three conditions are met. So first off, f of c is defined. So when we say that, it means that I should be able to choose the value of c, substitute it into the equation of f of x, and get a output value back out. And if that happens, that means that somewhere on the graph at x equals c, there is a actual defined point plotted on that graph. Whether it's a part of a continuous curve, that has to do with the other two conditions. So just this first piece of information tells us that there's a point on the graph at x equals c. Second piece, the limit as x approaches c of f of x exists. So remember, just based off of the definition of a limit that we've explored over the last two sections, whether the limit exists or not has nothing to do with whether there's a defined point. So these two things operate independently of one another. So just because we say there's a point doesn't necessarily guarantee that when I explore the limit, that the limit is approaching that defined point. Again, we just saw an example up top here where this function, the limit does exist. It would be approaching this y value, but that is not the function's value at x equals c, because that is this other defined point. So these two conditions both have to be true, but one doesn't imply the other. That's why we have this third condition. It's a way of combining the first two to guarantee that the function ends up being continuous. So if the function is continuous, then the limit of f of x will be equal to the defined point at x equals c. So having this third condition in here rules out this third possibility from up top. So having that guarantees that the point that we are approaching from either side of x equals c is the defined point for the function f at x equals c. So that's for continuity at a point. So now we have to talk about at more than one point, so across an entire open interval. So a function is continuous on an open interval from x equals a to x equals b if it's continuous at each point in the interval. So essentially what that means is for every value of x in this interval, you should be able to go through and check off all three of these conditions for every single value of x. Now, theoretically, that would take an infinite amount of time because between any two values of x, there's an infinite number of points I would have to check. So we're never really going to go about this by checking every single value of x. Instead, we have rules for different kinds of functions, different rules that we can't break that we want to look for possible values of x that may break them, and then that limits the list of values that we actually have to check for. So a function is continuous on the entire real number line or everywhere continuous if the open interval that we're continuous on is all real, so from negative infinity to infinity. That happens when we are working with well-behaved functions. So you've heard me say that before. These functions that are continuous everywhere, these are the really easy ones to work with. This is what you've spent most of your time in algebra classes exploring. These would be things like polynomial functions are continuous everywhere. They have a domain of all reals, which means you can pick any value of x, substitute it in. And because we can pick any value of x and plug it in, that means we're not skipping over anything and we never produce any kind of discontinuities. Now, one little note to add in with this, notice that it says open interval and not closed interval. Remember the idea of these intervals. Open intervals means we're not actually including the endpoints of the interval with whatever it is we're talking about. So in this case, continuity. So we can't actually say that a function is continuous on a closed interval because in order to do that, you'd have to be able to check the three conditions for x equals a at the beginning and x equals b at the end of the interval. And because they are endpoints, we wouldn't be able to evaluate the limit as x approaches c because they're endpoints. So we'd only be able to check a coming in from the left side. So if you imagine a number line, x equals a, x equals b, we would only be able to check the limit as x approaches a from the left side, or excuse me, from the right side. And then for b, the opposite would be true. We'd only be able to evaluate it from the negative side of b. So because we can't check both sides, we can't check the limit condition, and therefore we can't check the continuity definition for those endpoints. All right, now let's talk about types of discontinuities. So there's all kinds of craziness that can happen with these graphs, but three major types of discontinuities that some of them we've already talked about, but now we're going to do it in a little bit more formal way. So the first of those is a vertical asymptote, or the more technical name for that is a non-removable discontinuity. So we refer to it as a non-removable discontinuity because in the equation, there is no way to remove the restriction on x that produces the vertical asymptote. So because of that, that's where the name comes from. So we end up with a vertical asymptote actually showing up on that graph. So that is that imaginary line. We often draw it with a vertical dotted line. So for example, something like this. So that would be a value of x that is removed from the domain. It works everywhere else. And then we often see some craziness going on around it. A lot of times we have horizontal asymptotes with these rational functions that commonly produce vertical asymptotes. But horizontal asymptotes are something to do with the y. Vertical asymptotes have to do with the x's. So this would be a value of x that we removed from the domain. And when we remove it from the domain and it produces that asymptote, we see information, valuable information that comes into play as far as limits go. So whenever there is a vertical asymptote occurring on a graph, that means that the limit as x approaches that value c of f of x, it's going to approach either positive or negative infinity. And because it's doing that, that is the telltale sign. When we see that, when we evaluate a limit and we get positive or negative infinity as we're approaching a finite value of x, that's our telltale sign that we have a non-removable discontinuity or vertical asymptote. Second type, a hole in the graph, a removable discontinuity. So again, that's the other side of it. So when there's a hole in the graph, that means that there is some kind of algebraic manipulation that we could do to rewrite the original function in a new form where that restriction of x no longer exists in the way that we write it, but it did exist in the original form. So that value of x is still taken out of the domain, but we removed it from the graph. So that's different from the vertical asymptote. This is a value of x that was never going to be able to be used in any form of the original function. So because of that, that's why we have that vertical asymptote in there. But a hole is just simply a point, a single value of x that we removed, but the limit of f of x still exists as we approach that value of x. So that's the big difference. So vertical asymptotes, the limit doesn't exist because we're going to the infinities, but for a hole in the graph, a removable discontinuity, the limit does exist. It's just that f of c is not defined at that point. And then the last type, the jump discontinuity, this is the third one that we looked at above. This is where the limit does not exist at x equals c because we have different one-sided limits. So from the left, we are approaching one y value, and from the right, we are approaching another. Now, one of these points may be defined. That part actually doesn't matter because the limit not existing is the major issue here. So whenever there's a jump, I have to jump down to the other piece to continue tracing. That is a jump discontinuity. So the function's discontinuous at x equals c. All right, so now we're going to take a look at some examples of where we actually need to test for continuity for a given function at particular values of x. So for our first one here, we have f of x equals x squared minus 3x minus 4 over 3x squared plus x minus 2. And we're going to be testing at the value x equals 1. So this is a rational function, and just to refresh your memories, remember rational functions can have some weird things that occur on their graphs, mainly asymptotes and holes. Not every rational function has those, but most of them have some variety of those. So even though that's true, it doesn't mean necessarily that the value of x that we're concerned with has one of those weird things. So just because you're working with a particular function that you know is likely to have those things, you have to be careful in just assuming automatically that the value of x you're investigating is where one of those things exists. So that's why we have the definition. I've already put the three conditions here so we don't have to flip back and forth. So we're going to refer back to these as we go through these problems, okay? So first condition here, I need to see, does f of 1 exist? Is there a value of this function at x equals 1? If there wasn't, then that means that this guy breaks some kind of rule when I plug 1 in, and that would mainly be making the denominator equal to 0. So let's test it. If I plug 1 into the numerator, I get 1 minus 3 minus 4, so negative 6. 1 into the denominator gives me 3 plus 1 minus 2, or 2. So we do get a finite value, negative 3. So that means the first condition passes. This function has a point at x equals 1, and the y-coordinate is at negative 3. Second condition, we need to evaluate the limit, or see if the limit exists as x approaches 1 for this function. Well, we just checked the value of the function. We checked to see, is it possible for me to plug x equals 1 into the function and get a value out? And remember that when we try to take the limit of a function, that is the very first step. Does direct substitution work? And really the only time that direct substitution could work, but the limit still not exist, is with a crazy looking function like this guy down here, piecewise. But all these other function types that we work with, polynomials, radicals, rational functions, exponentials, logarithms, all of those guys, none of them really have any crazy broken pieces like a piecewise function does. None of those have those things naturally occurring. So it is safe for us when we check this first step, if we go to check the limit of one of those typical functions, we know that this limit is going to exist, and that's because direct substitution with this function works, and we would be getting negative 3 again. So the second condition passes, and because these two both equal the same value, we know the limit as x approaches 1 of f of x is equal to f of 1. And so our third condition passes, and this function is continuous at x equals 1. So even though this function does have some crazy stuff going on, the craziness is not actually occurring at this particular point. So 1, -3, somewhere down here. So this guy's got some crazy stuff going on, asymptotes, vertical asymptotes and horizontal asymptotes, but none of it is occurring at our particular point. The graph's just going to be a normal looking graph around there. All right, our second one, we've got f of x equals 4x cubed minus 5x squared plus 9x minus 3, and we're testing at x equals 2. Well, this one's pretty easy. This one we know to be continuous at x equals 2 because this is a polynomial function. And polynomials are the easiest of all the different functions that we work with. There is never going to be a polynomial function that does not have a domain of all reals. And there is never going to be a polynomial function that is not continuous everywhere. So if you are lucky enough to be given a polynomial function and asked, is this function continuous at a value of x? Well, the answer is always yes. Doesn't matter what the value of x is, polynomials are continuous everywhere. Polynomial functions cannot have vertical asymptotes. They can't have holes. They can't have jump discontinuities. None of the crazy things that we've looked at so far, none of those things exist on the graph of a polynomial because they are continuous everywhere. So it's just kind of like a automatic thing for us. So it's nice that we don't have to waste any time checking the steps for those. All right, but now this big, crazy looking thing. So remember, a piecewise function is just we take parts of different functions and kind of put them all together to make a crazy looking graph. Sometimes when we transition from one piece to another piece, those parts will match up and continue on. In that case, this would be a continuous function because where one piece ends and the next one begins, they meet up. But other times that won't be the case where one ends, the next one jumps and begins taking off from there. So it's not a guarantee which one of those we have. We have to do a little bit of work to actually check to see which one of those is occurring. So first what I want to highlight, so there are 3 intervals, and then this second line here, it's not an interval that we're using this piece. It's actually just one particular value of x. So without doing any kind of work, looking at how this function is defined, I know that at -2, there is a point up here at y equals 4. Now, whether that point lies on 2 connected pieces or lies on the curve, it may not lie on the curve at all. We won't know until we actually do a little bit more work with this guy. But that's how it looks. When we only have x equal to 1 value over here, then that's just defining a single point. These other 3 are intervals of x values. So these other 3 are defining curves or pieces of curves that we're going to plot on this graph. Now, I do want to point out the 3 functions that we're using for those intervals are all polynomials, linear, quadratic, and another linear function. So what we don't have to worry about here is any kind of crazy stuff going on in those pieces. This would be continuous everywhere on its interval, so would these guys. So the 2 values that they asked us to actually check for are the transition points. So at -2 and then +2, we want to know, do these pieces match up or are they going to be disjointed, and is there a jump discontinuity? So let's check x equals -2 first. So first off, again, we're going to go through the conditions. So we need to know, does f of -2 exist? Well, yes, it's defined here. If I plug -2 into the function and I go over here to try and figure out which line I'm actually going to work with, that would fall on the second line because that's where x equals -2. So I know the answer is 4. So the first condition passes. For the second condition, so this is an example of where I can't just say that, well, direct substitution would have given me the same answer as the first condition, because we know that's not necessarily the case here. These are pieces, so we need to make sure that the pieces on left and right of x equals -2 line up and that the limit exists. So to answer this, we actually need to check one-sided limits. So we're going to check the left side of -2 and then check the right side of -2. So to the left of -2, or when x is less than -2, we are using this guy. So the limit of that piece, we can use direct substitution here, but we're going to plug it into the first function that's listed here. So that would give me +6 minus 5, or 1. So what that tells me is on the left side of -2, this linear function is approaching y coordinate of 1. So it's going to look something like that. Okay, now I know it's an open dot there too because -2 is not actually included in the interval. Then from the right side of -2, that would be on this interval, x squared minus 3. So when I plug -2 into there, I get 4 minus 3, or 1. So the two one-sided limits match up, and so the limit does exist, and it is +1. So I know on the right side of this, I have this quadratic function. But remember, it's only part of the quadratic function, so we're going to start here, and I know it's opening up, so it'll look something like this for now, okay? So the second condition passes, but now when we go to evaluate the third, we know this guy is going to fail because the limit as x approaches -2 is not the same value as the function's value at -2. So we have a hole here because neither interval is including -2, and we redefined the point of the function up above at +4. So because these two failed to equal the same value, the third condition fails. So we know the function is not continuous at x equals -2. All right, but now let's check x equals +2. Let's see what's going on the other side. So for this one, we don't have to worry about an extra point. This one's really just focused on, are these two portions going to meet up? So for the first part, we need to know what the value of f of 2 is. So looking at the two intervals, the quadratic portion doesn't use +2, but the linear in the bottom does. So when I plug that in, half of 2 is 1. So I know for sure at 2, 1, there is definitely a point there. It's it's where the last portion of this graph is going to start. So I know it's going to start here and then take off. Now for the second part, or second condition, we're going to look at the limit as x approaches +2, but just like before, we need to look at the left and right-sided limits. Oops. So for the left-sided limit, again, that means we're going to go back to the quadratic function. Notice I didn't finish this part because I wasn't sure where we were going to end up until we actually check it. So let's go back and do that. So for the left-sided limit of 2, that would be in this interval. So if I plug +2 in, I get 2 squared minus 3. That's also equal to 1. So I can now complete this guy. I know that this one is heading towards 1. And we use direct substitution to find the value of this function in the second interval. And that's what we're going to have to use here for the right-sided limit. Positive or values greater than 2 are in this interval. So we're going to use this function, so we get 1 again. So the one-sided limits match up, so the overall limit is defined. And because these are equal to the same thing, we know the limit exists, and its limit is the value of the function. So the third condition passes, so we can see the function is continuous at x equals 2. The next one says f of x equals the cube root of 4x squared minus y, and then we're going to check that one at x equals 3. So typically when we see a radical, our alarms start to go off, everyone starts to freak out, and they think that the cube root is as difficult to work with as the square root, but it's actually not. So if you remember, square root functions have the restriction that the inside of the radical, or the radicand, has to be positive or 0. You just can't have negatives inside, which will restrict the domain and can cause some issues with discontinuities and that kind of stuff, especially when we start to put crazy stuff inside of the square root. But the cube root does not actually have any of those issues. If you think back to the parent function of y equals cube root of x, that's like raising something to the 1/3 power, and we can take the cube root of any real number. So the domain of this guy is all reals. This is actually a well-behaved function. It's a funky looking graph. It's like a sideways cubic function. Okay, it looks like that guy. So the parent function has a domain of all reals. Then we would have to analyze the inside of here, 4x squared minus 9. That is a quadratic function, which also has a domain of all reals. So when we take a composition, or we take one function and put it inside of the other, which is what we're doing in this case, we're taking the quadratic 4x squared minus 9 and substituting it inside of the cube root function. When both of those domains are all reals, we don't have to worry about what 4x squared minus 9 is going to produce and then make us take the cube root of it, because we can take the cube root of anything. So this is another one of those well-behaved functions, just like the polynomial above, where we know that this guy is going to be continuous everywhere, including that value of x that we want to check. Now, if we wanted to go through our three conditions still, we could. First condition, f of 3. That means I got to plug 3 in, so I would get 9 times 4 is 36, minus 9 is 27. Cube root of 27 is a real number, that is 3. Second condition, the limit as x approaches 3. Well, again, it's not a piecewise, so the direct substitution method would work here as long as I get an answer, and I know that I would because I just got an answer by substituting 3 into the function, so I know it's 3. Both of these guys are the same value, so that third condition passes. So we know this function is continuous at x equals 3, and it happens to be that it's continuous everywhere. So now that we know how to determine if a function is continuous at a single point, now it's important to discuss continuity along an entire interval. So a function is continuous on an interval if the function is continuous at each point in the interval. Again, most functions that we've seen before in the past and worked with, those would include polynomials, rational functions, power functions. Power functions are really just single x squared functions, exponential, logarithmic, and even most of our trig functions, except tangent and the reciprocal ones, are continuous on all points within their domains. So those are considered well-behaved functions because if we pick any value of x equals c that's actually in their domain, then that third condition for our test for continuity is true. And again, that is saying that the limit as x approaches c of f of x is the same thing as the value of the function. So essentially, this wipes out that third possibility of where we have a hole in the graph and a point defined elsewhere. So as long as we work with these kinds of functions and we pick a value of x that's actually in their domain, then we're guaranteed that the function is going to be continuous at or on that entire interval for the domain. There are some other functions, though, that are not well behaved to begin with, but sometimes we can actually fix them by creating a piecewise function where we define an extra point that kind of fills in the hole that's causing the discontinuity in the first place.
So for these examples, we're going to kind of focus on intervals for continuity. So for this first one, we're going to take this piecewise function and identify all the intervals for which it is continuous. So remember the idea of a piecewise, we've got 3 pieces of different functions. So we're taking the entire interval from negative infinity to infinity and breaking it up into 3 pieces. We have transitions at x equals -1, a transition at x equals 4. So those are our 3 subintervals. And the first piece is going to be a linear function. Second piece, some kind of cubic or part of a cubic graph. And then the third piece is another linear function. So the big takeaway here is we know, because all 3 of these are polynomials, that we don't have to be concerned with any possible issues of discontinuity within each of the 3 pieces. The only places that discontinuities could possibly exist would be where we transition from one piece of a function to the next. So that's where we're going to focus our attention. So again, if you think about the 3 conditions, so for the first condition, we're looking for, does f of c exist? Is it defined? Well, at -1, we're including -1 in this first interval, and we can plug it in. So that condition passes for x equals -1. Then for the second condition, we're thinking about the limit as x approaches c for f of x. Does that exist? And so for that one, that is going to be the big concern here, because again, limits have to be evaluated from the left and the right side, which is especially important with the transition points on a piecewise function. So to evaluate this or check this condition, we actually have to think about the limits at these transition values, which basically just means I need to figure out what's the y value approaching for the first piece and the second piece surrounding these two x values. So to the left of x equals -1, that's going to be 3x plus 1. So if I want to evaluate the limit as x approaches -1 from the left, I would need to use 3x plus 1. Oh, not sure what happened there. So because these are all polynomials, we know we can evaluate using direct substitution. So if I plug -1 in there, that would give me -2. So that actually gives me an idea of what this first piece is going to look like. So it's going to be a linear function that is approaching the point -1, -2. So that's the limit from the left side, and then the limit from the right side of -2, well, that would be this middle interval. So I would be using the cubic function there. 4x squared plus x plus 6. So if I substitute -1 in there, that would give me -1 minus 4 minus 1 plus 6, or -1 or 0. So the fact that those two one-sided limits do not meet up at the same place tells me that that condition fails. So at -1 coming from the right side, I know this function has a hole because -1 is not included there. It's a hole on this piece of the curve, but it's still defined down here. And then we're jutting off into some part of this cubic function. I don't know exactly what it looks like. I know it's got a y-intercept of 6 up top here. So we're just going to sketch it out. Let's say it does something like that for right now. All right, now so that tells us at -1, this function is discontinuous. We have a jump discontinuity at -1. So now let's check 4. So same idea, 4 is defined using the bottom interval, so this bottom piece in the third section. So the first condition passes. Now for the limit, so we're going to check the limit as x approaches 4 from the left side. And so to the left of 4 would be on this cubic function again, which means I got to write this whole big long thing again. And now I get to do some big old mental math. So 4 cubed is 64, minus 4 times 4 squared, that's 64 plus 4 plus 6. So that gives me 10. So this function is approaching a y value of 10 from the left side. So let me fix this a little bit. So it's probably going up something like that. Let's say 10 is right there, and I know it would be a hole because 4 is not actually included in that interval. And then the limit as x approaches 4 from the right side, that would be the bottom interval. That would be the linear function down here. So plugging 4 into there, that would give me -2 plus 12, which gives me 10. So that means that the limit of this function does actually exist because we are approaching the same thing from both sides. So when I go to plot the third piece, even though this was a hole when I plotted it for the middle portion, because the function is defined at 4, that actually means I'm going to fill this in with the defined point for the bottom portion of the graph, and then graph -1/2 x plus 12 from there. So we can see that the cubic function meets up with the linear function. So the limit does exist. It meets at the defined point because 4 is included in this interval and there's no other points defined elsewhere. So the function is continuous at x equals 4. So now if we want to describe all intervals where this function is continuous, we can say that the function is continuous on the first interval. So it's continuous on this whole first piece of the linear function, which would go from -∞ up to x equals -1. We're not including -1 because that is the discontinuous value. And then instead of having to list these other ones separately, because we make a continuous transition at 4, we can actually join this set with the other interval from -1 to +∞. So we don't have to break the second pieces apart because they were actually continuous there. We can just list one longer interval. And that is it. Those are the two intervals where this function is continuous, or another way of saying it is everywhere except x equals -1.
For this next problem, we're asked to identify which of the four functions given here are not continuous on the open interval negative infinity to infinity, or remember that's just another way of describing the interval of all reals. So essentially, one of these guys has a value of x that is restricted in the domain. We have to identify which it is. So for the first guy, f of x equals 1 over the quantity e to the x plus 2. Anytime that we have a rational function, again, that moniker is really just an all-encompassing thing for fractions. So when the original function has a fraction where you have the variable x somewhere in a denominator, there are potential restrictions because the big rule with fractions is you can't divide by 0. So we have to always explore values that make the denominator equal to x. So in this case, we're focusing on the function e to the x plus 2 and where that could potentially equal 0. So there are algebraic ways to solve just about any equation that I could throw at you guys, but a lot of times it's really helpful to explore solutions of equations by thinking of what their graphs look like. So when we set the function e to the x plus 2 equal to 0, what you're really doing is looking at where this function has a y value of 0, or in other words, hits the x-axis. So to explore that, let's just think about this in terms of transformations. So the function e to the x is that parent exponential function. So we have a horizontal asymptote on the x-axis, y-intercept of 1, and then exponential growth takes off for us. So to create e to the x plus 2, we're essentially taking all of the points on that graph and vertically shifting up 2 units, which means that the horizontal asymptote that was on the x-axis is now up 2 units. So what does that mean for us? Well, that means that this function never has a y value at 2 or below. So there is no way for this function to actually equal 0. So that means it's impossible for us to ever substitute a value of x into this function, and we are forced to divide by 0, which means there are no restrictions on this function. This is a well-behaved function, domain of all reals. There are no restrictions on x whatsoever, so no vertical asymptotes. It's not an absolute value function or already defined piecewise, so we don't have to worry about jump discontinuities, and there were no common factors removed top and bottom, no indeterminate form or anything like that, so we don't have any holes here either. This is a well-behaved function, so this is continuous on all reals. So this one's not our answer. G of x equals x cubed minus 4x squared plus 7. Well, right off the bat, you should notice that this is a part of the polynomial functions family. Domain of all reals. This is the prototypical well-behaved family of functions, so this one is continuous everywhere as well. Next one, x minus 1 over x squared plus 3x minus 4. Rational function, polynomial over polynomial. Definitely a chance that something could go wrong here. We could have a discontinuity. So again, just like we did for the first rational function, we are going to explore what could possibly make the denominator equal to 0. This is a quadratic function, so we could try to factor this guy. Numbers that multiply to make negative 4, add to make positive 3. Those would be x plus 4 and x minus 1. So there are two values of x that we must restrict here, negative 4 and positive 1. So there's more exploration that can be done here. There's a common factor top and bottom, which means this guy is going to turn into a hole. This would be a vertical asymptote. That's just nice information to get into a routine of identifying when you come across it. But to answer this question, all we really need to identify was that this function is discontinuous at two values of x. So this is the function we were searching for. Now we didn't get to it, but just to explore, k of x equals 4 cosine of x minus pi. This is a transformation as well, similar to how the first function was a transformation. So is this one. So the parent function y equals cosine of x is a well-behaved function, has a domain of all reals, starts at 1 and goes down. There's our wave and then backwards. So that's the parent function. The 4 out in front is a vertical stretch. So this is going to be 4 times as tall as the original. And then x minus pi, that is a horizontal translation or horizontal shift to the right, pi units. But none of that impacted what values of x I'm allowed to substitute in. The stretched version still has a domain of all reals, and the shifted version would still have a domain of all reals. There are no vertical asymptotes or holes anywhere, so this guy would also be continuous on all reals. All right, let's take a look at another one here when thinking about intervals. So same idea, but instead of being the interval of all reals, now we have a restricted interval from 0 to 4. But the idea is still kind of the same. We want to explore where these functions are discontinuous, if anywhere, and then see if those values line up with the given interval. Because there is a chance that some of these might be discontinuous elsewhere, but just not in this interval. So for the first guy, rational function, polynomial over polynomial. So basically what we just did for h of x above, let's factor this denominator, x plus 2, x minus 2 equals 0. So this guy would have a domain of x cannot equal -2 or +2. So in this case, that x minus 2 factor would remove itself. So +2 would be a hole, and then -2 would be the vertical asymptote. But again, -2 does not fall within this interval. So the only issue here that would be relevant to this interval would be the 2. So on this interval, this guy's got the vertical asymptote at -2. It's a small degree over big degree, so horizontal asymptote at y equals 0. So this graph looks something like this guy, okay? And then the hole at x equals 2, well, if I plug that into the resulting function, 1 over x plus 2 would be 1/4, so there would be a hole right about there. And so on the interval from 0 to 4, that function is discontinuous at that hole. Okay, so again, the only way that we could fix that hole is if we made this into a piecewise and defined an extra point at the coordinates 2, 1/4, but we don't have that. So this one would not be the continuous function that we're looking for. All right, let's check g of x. Same idea. This guy would factor to be x plus 3, x minus 3. Domain here would be x cannot equal -3 or +3. So again, that +3 value exists within this interval. In this case, that would be the vertical asymptote that's left behind after the x plus 3's get canceled. So this is not the function that we're looking for. But h of x, x plus 3 over x squared plus 9, this one is always a tricky one. Remember, there is no factoring method called sum of squares. There is a difference of squares technique and a sum of cubes, but there is no sum of squares. And that's because this guy isn't factorable. Another way of proving that, if I try to use another method, x squared plus 9 equals 0, I could try to solve using square roots. If I subtract 9 from both sides and then square root both sides, I would get plus or minus the square root of -9 is really 3i. So there is a solution, but the solution is a complex number and not a real number. So we don't have to worry about this guy in terms of this interval. So what that means, well, using real numbers only, that denominator cannot ever actually equal 0. So this domain would be all reals. This would be a well-behaved function. Still has a horizontal asymptote at 0, but no vertical asymptotes, holes, or jump discontinuities. So this would be the guy that we're looking for. Just to explore this last one, again, tangent of pi over 4x. This would be a tangent function, which if you guys remember, normally has restricted values at the pi over 2's. So the normal domain for tangent is x cannot equal pi over 2 plus n pi. But if I manipulate that argument with that b value of pi over 4, then we have to solve this guy. And let's see, we're going to take pi over 2 plus n pi, divide all of those by pi over 4, which is just like multiplying all of this by 4 over pi. So we would get the new domain to be x cannot equal 2 plus 4n. So those create the pattern of asymptotes. And so one of these values, when n equals, let's see, when n is 0, I plug 0 in for n, we would have a vertical asymptote at 2. So that would be where this first guy on the right side ends up being. Goes from -2 to 2. That would be a restricted value within the given interval, which is why this function fails as well. For our final topic in this section, we're going to talk about how we can work to fix discontinuous functions. So some functions are naturally discontinuous at certain values of x, and depending on what kind of discontinuity they have, it may be possible for us to redefine the function so that it becomes continuous. So this is mainly referring to removable discontinuities. So if I have a hole on a function, it is possible for us to redefine it as a piecewise function and be able to fix that, basically fill the missing point. So if the limit of a function exists at a discontinuity in its graph, then it's possible for us to remove the discontinuity by redefining the value of the function at that point. So again, this is the type of graph where the function would be undefined, but the limit of the function still exists at whatever this value of x is. So in order for a piecewise function to be continuous at a boundary to the partition of its domain, the value of the expression defining the function on one side of the boundary must equal the value of the expression defining the other side of the boundary as well. Basically saying that if it's a piecewise function to start, then when we transition from one piece to the next, the limit needs to exist at that transition value. If the limit doesn't exist, then there's no chance of the function being continuous, which we've already seen several examples of that in this section. So let's dive in and try a couple of these. So for the first one, we're going to start with a piecewise function, and we are missing the transition value. So let f be defined as below, where k is some constant. We want to find what value of k makes f of x continuous. Okay. So basically, we just need to know where these two functions intersect. Because if no matter what these graphs look like, where we stop one and continue the next, if we stop the interval of the first graph before it has intersected the second graph, then we wouldn't ever have a chance of being continuous. Then it would look something like this. I stopped here and then make a jump up to where the other guy would be, or below if that were the case. And what's not a possibility is for us to transition after they intersect. Because if I were to try and do that, if I were to move past the point of intersection on the first piece, I can't jump backwards in my interval and start the next guy over again. So this is always either going to be they stop before they intersect or they stop when they intersect. So we want a continuous graph. So we're trying to explore where these two functions meet one another. So the easy way around this, or to solve this, is we basically want whatever the first function equals when x is equal to k to be the same thing for the second piece. So we basically just plug k in for x into both pieces. That is going to result into an expression with k in it for both pieces. And we're just going to set these two expressions equal to one another and solve. So now this first problem with this process is pretty simple because we have basically just a linear equation. So we'll add 2k to both sides, add 2 to both sides, and then divide. So we're going to get that k equals 1. Or if we explore this graphically, I punched both of these into Desmos, so looking at their whole graphs. So the only way that this becomes a continuous piecewise function is if I restrict the domain of the first up until 1, and then restrict the domain of the second after including 1. So there we have a continuous function. Again, if I were to alter this value to anything before x equals 1, say x equals 0 for both of these pieces, now we have this jump discontinuity where there's no chance for them to be connected because we stopped the pieces before, or we made the transition before the functions had a chance to meet up with one another. All right, now let's try and fix a function using a new definition as a piecewise. So the following function is discontinuous at x equals -4. So they're straight up telling us where the discontinuity is, or one of them anyways. We want to know how could the function be redefined as a piecewise function to make it continuous everywhere. Okay, so let's explore this rational function a little bit more. So one discontinuity is at x equals -4. And if you notice, when I substitute that in, it makes the numerator equal to 0. So for that to be a discontinuity, that means x plus 4 must be a factor of this denominator as well. So let's explore factoring this guy a little bit. So AC method would give me -8. Whoops, that is not -8, sorry. So that would give me -8 for the product, and then my sum needs to be +7. So that would be +8, -1 are my two values. So let's factor this guy, 2x squared, 8x, negative x, and negative 4. So I can factor out 2x, leaves me with x plus 4. Negative 1 leaves me with x plus 4. So my two factors are 2x minus 1 and x plus 4. So that factor of x plus 4, that is the removable discontinuity. So they didn't specify that in the problem, but that's really important for us to identify, because if negative 4 was a non-removable discontinuity or a vertical asymptote, then there is no chance of making this function continuous. Okay, we can only fix the piecewise, or using the piecewise method to fix a hole. Okay, so to do this, we are going to redefine, or let's look at the new version of this one. We're going to have to alter these directions just slightly. But the new result of this function is that f of x is equal to 1 over 2x minus 1. And we're going to add an extra restriction on here that x cannot equal negative 4. We tend to write it that way because looking at this new version, it doesn't show that that restriction is there, and that's why we're adding it on there. So we remind ourselves there's a hole there. So the directions here say make it continuous everywhere. I'm just going to kind of skip over that part because this guy has a vertical asymptote, so it's not actually possible for us to make it continuous everywhere. Okay, so we're going to basically we're just fixing this removable disk continuity, the hole. But we need to know what coordinates the hole has. So what we do know right now is this function still has a restriction at positive 1/2. So that's where the vertical asymptote would be, at positive 1/2. And at negative 4, there is a hole on here somewhere. We have small over big, so we know the horizontal asymptote is at y equals 0 on the x-axis. So to find the coordinates of the hole, again, we plug negative 4 into the new resulting guy, and that will give me negative 4 for the x and 1 over, let's see, negative 9 for the y coordinate. So negative 4, negative 1/9. I know the hole is somewhere down here. And we're just going to speed through the rest of this. The rest of that guy looks something like that. And the other piece is going to be up top in the right corner here. So rough sketch, that is what our function currently looks like. So again, it's not going to be continuous everywhere, but it can be continuous everywhere except the vertical asymptote. So basically, I want to fix that point. So the way we do that is I'm going to make this a new function, g of x, and when f of x is equal to any value of x that is not equal to negative 4. So everything else, then we're going to use the original graph. Okay? But if it's not equal to negative 4, or excuse me, when it is equal to negative 4, then we have to fill in that missing hole. So that missing hole has coordinates of negative 1/9. So right now there's a missing point, but by defining this extra point on the, or using the piecewise version, we are able to actually fill in the graph at that missing point, which now makes it a continuous function everywhere except for that vertical asymptote. And for our last one, it says let f be defined as below, where c is a constant. We want to find what value of c, if any, makes f continuous at x equals 2. So this is a different variation of the first one on this page. So this time around, we know the transition value, but there's some unknown constant value within this second function, so the right half of this graph, that we need to find the particular value of that will make the two pieces match up. So as that value of c changes, the position and the overall shape of that second piece will change. So we want to know where these two guys are going to meet up, or what value of c will make them have a continuous transition at x equals 2. So we're actually going to kind of go about this the same way, though. So x is not an unknown value now in this situation. We have a particular value. C is the unknown. So to solve this, we need to make sure that when I plug 2 in for x into both of these, the end results from both pieces equal one another. So let's plug 2 into both of these. So for the first half, the left half of the graph, we would end up with 4 plus sine of 2. And we would want that value, whatever it's equal to be equal to what we get when we plug 2 into the right half, or the bottom function. So that would be c plus 2 natural log of 2 goes in for x. So the argument 2 plus c. So you see what we end up with is instead of an expression or a function that depends on the value of x, we set the value of x to be 2, and instead we have an equation that depends on the value of c. So now we just need to use some kind of graphing calculator device to help us solve this. So instead of using Desmos, I'm going to show you guys how we would go about doing this in your graphing calculators. So anytime that you want to solve an equation using a graphing calculator, again, you can really think of this graphically. This can be some kind of function. This can be some kind of function. And to solve an equation, you just set the two equal to each other, or we look for their intersection. The only difference about this is we're going to have to be careful because of the variables that your calculator will actually read. So in y equals, I'm going to get rid of this stuff. So the first half of the equation was 4 plus sine of 2. So I'm going to type 4 plus sine of 2. Now let's make sure that we're in radian. Make sure you guys are in radian when you're doing this. Technically, it doesn't matter, but when we're doing trig, it's always important that we are consistent. So 4 plus sine of 2. So that's just going to be a number. So y equals some number. It's like 4 plus something. So it's really just going to show up as a horizontal line on the graph. But then for the second piece, on paper right now, we are using c as the unknown variable. But your calculator can't graph in other variables except for the predefined ones. So on paper it says c, but we're just going to use x in the calculator in its place. Even though we replaced x with 2 a little while ago in this problem, we're only using x for the calculator. So I'm going to type in x plus 2, oops, all right, x plus 2 natural log of 2 plus, and then our unknown quantity, which was, again, in the calculator, x. So let's just double check. Yes, okay. So now I'm going to do zoom 6. That's the standard graph, just so I can see everything. So there we go. So you can see the blue line is the constant value of 4 plus sine of 2. The red curve is where the natural log function is meeting up with it. So now we need to find the intersection of that. So to do that, I would go second, trace. Under calculate menu, we want the intersection. So really, you just have to move your cursor using the left or right arrows as close as you can get it, or relatively close. And then we're just going to hit enter 3 times. Enter once for a value close on the first curve, again, close on the second curve. And then the third one is actually just a guess, which means you can move the cursor close to where you think it's going to be. That just helps speed up the process, but it's not necessary. So you can actually just hit enter anywhere, and it will snap right to that intersection value. So it says x equals 2.091, but again, on paper, that is really the value of c that we are missing. So c equals, and I already forgot what it was, 2.091. Oh, and everything wanted to glitch there, so let's try that again. 2.091. So what that means now, if I were to go back and regraph this again and plug that value in, we should see a smooth transition. Now, it might not be exact because I'm going to round this, but if I were to do 4 plus sine of x when x is less than 2, and then 2.091 plus 2 natural log of 2 plus, or sorry, x plus 2.091 when x is greater than or equal to 2. Now you can see that this graph has a relatively continuous transition. Again, it might not be exactly connected because I rounded the 2.091, but you guys can see to the naked eye, that is a continuous transition.